Welcome to the deep dive. Today we're going to talk about a really fascinating sequence. It sort of pushes the limits of combinatorial computation. It's the Dedekind numbers, listed as A000372 in the OEIS.
That's right. And our goal, really, is to unpack this number, often called M2. We want to explore its multiple identities and understand why finding its exact value is such a notoriously difficult problem in mathematics.
Okay, multiple identities. That sounds interesting. What are we talking about?
Well, what's amazing about M2 is that it counts three seemingly quite different things. It's the number of elements in what's called a free distributive lattice with n generators. It's also the number of monotone Boolean functions of n variables.
Okay, algebra and logic.
And maybe most intuitively, it's the number of antichains of subsets of a set with n elements, also called Sperner families.
Right. That equivalence connecting these different areas, algebra, logic, set theory, that seems to be the key insight, doesn't it?
Exactly. It's fundamental.
Before we dive into why it's so hard to calculate, maybe let's clarify those concepts a bit.
Yes.
Especially the Boolean functions and antichains.
Good idea. So for Boolean functions, monotone is the crucial part. It means if you flip an input from false to true, the output can only stay the same or go from false to true. It can't go backwards.
So they preserve a kind of order, like reliable switches.
Precisely. And these specific functions perfectly match up one-to-one with the antichains.
Okay, and the antichain definition, you said that might be the most intuitive?
I think so. Take a set with n elements. An antichain is just a collection of its subsets, but with a rule. No subset in your collection can fully contain another subset from the collection.
So if you pick two different sets from the antichain, neither is a subset of the other. They're incomparable.
Exactly. Incomparable.
Let's make that concrete. Maybe within two.
Perfect. If N2, our set is, say, XY, the Dedekind number M2 or A2 in OEIS terms is 6. There are exactly 6 such antichains you can form from the subsets of X, and each corresponds to one of the 6 monotone Boolean functions of 2 variables.
Okay, so like the Boolean function fxy equals a k n d y, that corresponds to just the single subset xy in the antichain.
Yes, that's the antichain containing only the top element x, y.
And the OR function, fxy equals x or y.
That corresponds to the antichain containing x and y. See, neither x nor y contains the other. They're incomparable.
I see. That clicks. But you mentioned this gets difficult fast. The growth rate.
Oh, spectacular. Dedekind himself calculated mn up to n4. That was back in 1897.
And after that, it became a bit of a computational saga.
A huge one. M5 is 7,581. That took until 1940 by Church.
Wow, quite a gap.
And then it gets much, much harder. M8, well, that wasn't computed until 1991 by Wiedemann. It's enormous, over 56 quintillion. Needed serious computing power.
56 quintillion. And M9, I heard that was very recent.
It's extremely recent, just calculated in 2023. 2 independent groups, one led by Zackel, another by Van Hertom. It really shows you the decades of work refining algorithms using massive computation just for N9.
So if N9 was that hard, what happens at N10? Is it just impossible?
Well, impossible is a strong word, but practically speaking, for exact computation, yes, currently intractable. There is an exact formula, believe it or not. Kisilevich's formula, it's a summation.
Okay, so why can't we just use that?
Because the number of terms in the sum is itself astronomical. For N10, the formula involves summing 10 terms.
2 to the power of 2 to the 10.
Exactly.
$224.
So exactly. $224. This number so large, it's hard to comprehend. Way, way more terms than atoms in the universe. Estimates put that around 10.8. You just cannot compute that sum directly.
Okay, that definitely puts intractable into perspective. So if exact calculation is out for N10 and beyond, what do mathematicians do? Give up.
No, never. We shift focus. We look for approximations, for asymptotic estimates. There's been great work here by people like Korshunov, Kleitman, and Markowski. They found very accurate formulas for how M behaves for large M.
And what's the key idea behind those estimates?
It turns out that most of the antichains, the overwhelming majority for large n, have a very specific structure. They mainly consist of subsets whose size is very close to n2, right in the middle layer of the power set lattice.
So even with this huge number of possibilities, most of the contribution comes from sets clustered around the middle size.
That's the crucial insight. It tames the beast, somewhat. It tells us where to look. The complexity is still immense, mind you. Counting antichains in general is known to be #p-complete, which is a class of very hard counting problems in computer science.
So this one sequence, A000372, really ties together logic, set theory, lattice theory, and pushes the boundaries of computation and theoretical analysis.
It absolutely does. It's a fantastic example of a deep mathematical problem.
Okay, so to wrap up this deep dive, the Dedekind numbers link these fundamental ideas through antichains, but calculating them remains this monumental challenge. So here's something for you, the listener, to think about. We have the exact numbers up to 9. We have amazing estimates for huge values of n. But that simple, elegant, closed-form equation for n, for any n, it's still missing. What kind of breakthrough, maybe even a whole new kind of mathematics, might it take to finally find it?